Mike, I'm really pleased to have you. Thank you for joining us at the No Show. How have you been coping in these crazy 3 months?
Hey, well, it's been a challenge. I'm one of those workers who's stuck at home doing working in my studies. You can see while I'm trying to homeschool my twin boys who are 9 years old and 9 years old, full of energy. And we've been sitting at the kitchen table doing maths exercises, and then I've been coming in here trying to do my research and trying to hold meetings with my PhD students. And so it's been a hectic time. And then it's key to get out and do exercise. That's one of the messages. This is how I work in educational neuroscience. We want to know about how to improve the plasticity of the brain, improve learning abilities in everyone. And one of the key things is about getting good sleep, getting good exercise. So I'm trying to make sure my kids get that as well.
So I suppose for you, I mean, I guess you can sort of use your research directly with your own kids, right?
I try, yeah, where I can do the translation of the academic research into actual practical tips. Indeed, so some of the activities we've been doing at our research center is to put information out there for parents about, because it's like the first time they've been sat down and had to do teaching with their kids. And I think we've all got a newfound respect for the challenges that teachers face. But just getting tips out there that, you explain something to someone, you explain something to an adult, and then they should know it, right? But that just doesn't seem to work with kids. You come back and they don't seem to understand it, and you keep repeating it, and then eventually they know it. So just getting information out there to parents that learning is kind of can be long and hard for kids, and it's all about keeping them motivated and avoiding frustration and trying to make learning activities relevant to kids, to give them plenty of positive feedback and sort of verbal positive feedback. Is very rewarding for kids. So these kind of things that we know about from academic research, trying to translate them into, say, activities sitting at the kitchen table when we're working with them.
And so is your background in neuroscience or is it in education?
So yeah, my background is in psychology, particularly what's called cognitive neuroscience. That's trying to understand how the mind works, taking into account what we know about brain function. So we think about androids and robots and computers. There are many possible ways that we can have thinking machines or thinking devices. But the way humans actually think is very conditioned by the fact that we're thinking with our own brains. And those brains have particular biological properties, which means we're good at some things and not so good at other things. In fact, what's interesting for me is education in terms of the brain is really a kind of Johnny-come-lately thing. If you think about our evolutionary history, these kind of cultural practices of putting ourselves in, or putting our kids in very particular environments to teach them skills like mathematics or reading, we just invented that stuff in the last few thousand years. And if you think what brains are really for, if you go back and look all across the species, across evolutions, brains are fundamentally for movement, to enable creatures to be able to move and carry out purposeful activity in their environments in order to feed, defend themselves, to mate and so forth. So the number one priority of brains is, believe it or not, is movement. If as an organism you don't need to move, then you don't need a brain. So trees don't have brains, right? Jellyfish just float around. They don't have a central nervous system. And the number two priority for brains is emotions, our relationship with other people, making sure that we're meeting our fundamental needs. Number three priority for brains is other people. That's because we're social primates. We move in groups. We're really bothered about what other people think and say and what they're about to do. So big parts of our brain are just involved in processing, thinking about other people, looking at their eye gaze, their body posture. So those are the top three priorities of what brains are for. And then you got to squeeze in the bottom this stuff about, and you got to learn to read, and you got to learn about science, and you got to learn mathematics, and learn how to play football and stuff like that. All of that is being layered on top of these more important priorities in terms of brain function.
That's very interesting. So for example, you mentioned there's these three priorities. So has there been research done that I suppose marries the idea of like learning with one of the top three priorities? So the importance of people or emotions, so that you can speed up learning.
Yeah, so what we need to do, we can't just ignore those priorities. We need to find a way to align those priorities with our learning outcomes. So to make sure that movements we carry out are the ones relevant to the task at hand, be it kind of handwriting or in counting on our fingers, or these kind of things. We need to make sure that the emotions that we have are pushing in the same direction as the learning outcome. So we don't want kids to be anxious about mathematics. We want them to be curious. Mm-hmm. So these are positive emotions which are not getting in the way. When we're stressed, when we're anxious, we're not in good condition to learn. And in terms of other people, we understand that there's a relationship between teachers and pupils. So we also know that kids can work in peer groups and kind of teach each other and work with each other. So trying to bring together all of these other priorities to align with our learning outcomes is the best way we can go.
Mm-hmm. So looking at I suppose that there's all sorts of lines of inquiry when it comes to education and neuroscience. What have been the areas of priority for your research?
So I can give an example of one project we've been working on recently that started off with a basic piece of neuroscience research, some data that came out of brain scanning research, and has ended up with us designing and testing a classroom learning activity. And that revolves around our ability to understand and think about what one might call counterintuitive concepts. Mm-hmm. So things like, we have everyday experience of things. So we believe we understand them. And then we sit down in a science class and we're taught something different. So if you think about young kids, as far as they can tell, the world is flat. So they go out and play football on the football field. That seems really flat, right? And then they sit in science class and all of a sudden they're told the world is round. And it doesn't seem round, but, in terms of our scientific knowledge, we're going to understand about planets and solar systems and so forth. You have to understand that the world is round. So there was some research done in neuroscience to show, how do we'll call them expert scientists, but actually this was done with undergraduate students in physics. How do they reason about counterintuitive concepts? And when they were put in brain scanners, it became apparent that part of what they're doing is inhibiting or suppressing this sort of intuitive knowledge in order to access their scientific knowledge. So you can't really see this, just in behavior, but actually what happens when you learn new concepts, say sort of scientific ones or mathematical ones, that you don't overwrite your previous knowledge. You add in the new sort of scientific knowledge alongside, and then in the right context, you inhibit, you suppress the irrelevant counterintuitive knowledge. So you don't want kids just to start thinking that the world is round all the time, because then they'll be rubbish at football, right? When they go back out and play football, the football pitch is flat. You don't have to change your mind about that. Mm-hmm. So that led us to develop an activity where we tried to train or help kids do this activity of suppressing the sort of intuitive response in favor of the actual kind of academic or scientific response. So, to give an example, if you say really quickly to someone, what do cows drink? You feel like you want to say milk because that's associated with cows. But of course, they're just mammals. They drink water only like everyone else. So we had this kind of computer game activity. It was structured a bit like a game show, and asking questions about sort of science questions or maths questions. So here'll be a maths question. You spend a lot of time learning that 5 is bigger than 2, and now you have to say, is a fifth bigger than a half? And he said, well, but 5 is bigger than 2, so maybe a fifth is bigger than a half. No, actually, that's different. Now we're looking at fractions. So we were training the kids in this game to do something called stop and think. Don't immediately give your first answer. Hold back, think it through, and then give you a kind of reasoned answer. So it was actually training a skill called inhibitory control, holding ourselves back. So I think teachers are familiar with this idea that when kids throw their arm up in the air to answer a question, actually, you don't want quick answers. You want kids to think about that. So we developed this learning activity, and then we took it out into schools. We visited about 90 schools, tested about 6,000 kids, where they had a term of playing this game, like 15 minutes, 3 times a week. And then we were able to show that this actually gave, I think, 1 month, equivalent of 1 month gain in maths, and 2 months gain in science on the kind of tests you do, SATs tests at the end of maths and science. So that started off with a neuroscience idea about the importance of inhibiting intuitive ideas when you learn new scientific or mathematical ones, and ended up with this actual demonstration that you play this game for a bit and you can get actual academic gains in tests on these topics.
And does this fall under this, like you mentioned before the recording, does this fall under the sort of bracket of cognition and improved cognition?
That's right. A lot of the educational neuroscience approach is, neuroscience isn't everything to do with education. We know education is a huge cultural enterprise. We know it's for society to decide what we should learn, what's important, what kind of skills that we want, for civilization or for our economy and so forth. The contribution of neuroscience is just to think a little bit about, we've done some decades of research now on brain plasticity, about how the brain changes to allow us to learn things. And maybe some of that kind of information could be useful for teachers to give them better tools in the classroom, a wider toolkit, and particularly to think about barriers that might get in the way of learning. So we understand some of that stuff about thinking about the brain as a biological entity. It's like an organ, right? So it needs the right amount of energy, and it doesn't want to be stressed out by stress hormones. And in the brain, particularly, sleep is important to consolidate learning and to refresh the neurons, as it were. So there's some of these factors that we can give advice about sort of good brain health. But there are other aspects where we're beginning to understand more about particular cognitive skills that can be improved through training. And so some of them are specific. So we know kids can struggle with learning mathematics if they don't have a good, what's called a number sense, an understanding of quantity. And if you try and build mathematics, all these symbols and operations and times tables, you don't have a good understanding about what different numbers are and how quantities fit together, and sort of what we would call a sensory motor understanding of quantity, then very quickly that the maths can get away from the kids. So for those kids, we need to sort of stop and make sure they understand sort of the basic identity of symbols and how they relate to each other and how they relate to quantities. There is a broader agenda of thinking about, are there particular activities we can get kids to engage in that will give them a benefit across all the kind of topics. So this is called cognitive enhancement. And there are a whole bunch of techniques out there. I wouldn't say there's any good evidence, really strong evidence of huge effects of any of these, but many of these techniques may give small benefits. So we're thinking about techniques such as mindfulness training or meditation training in classroom or relaxation training, about the possible benefits of learning a musical instrument, because it gives you kind of discipline, and you have to learn all these integration skills between kind of motor activities and reading music and learning melodies and playing in groups of musicians and so forth. So there's quite a lot of research going on in those areas. I think, interestingly, some of the strongest benefits appear to come from being physically fit. So about thinking about the brain needs to be getting the right amount of energy. And this is really a way to tweak PE classes. So when I was at school, PE classes all seemed to be standing in a line, queuing up to use the one piece of gym equipment, and then you kind of jumped over it or bounced on it, whatever it was, climbed up it, and then you went to the back of the queue. So most of the PE lesson was standing in queue. Now, if you're watching Joe Wicks, you get a better sense about what PE should be to improve physical fitness. It's got to be aerobically taxing. You've got to get out of breath. You've got to sweat. And thinking about if we make sure kids have enough of that kind of exercise, we see a boost in their learning. And that's just because as they're thinking, as they're learning, there's better delivery of energy to their brain to enable them to think.
So, I mean, I want to, like, exercise is obviously one of the most important things, and it's been spoken about a lot in sort of neuroscience and across the board. Has the UK, has the sort of national curriculum in the UK adopted these measures that for PE or for exercise that enhance education, and is that clear?
Yeah, I think everyone's moving in that direction. This seems to be an area where it's an easier win. There was a team in Oxford that's recently tried to run a randomized control trial where they wanted to focus on schools where they would bring in these regimes of particular exercises to improve aerobic fitness and compare them to some other schools where they had some more activities, maybe in PE class, but weren't designed to improve aerobic activities. Now, in a randomized control trial, this is the best way to see whether something works or not. You need your intervention group who are getting extra aerobic fitness training, and then you need control groups. And you need to do this across a lot of schools with, preferably several thousand children, just to see whether it works. And when the team from Oxford tried to do this, they had to tell some schools that they would be in the control group, that they wouldn't be getting the extra physical fitness training. And schools were really reluctant to be in the control group. They were so on board with the extra kind of aerobic training that it was difficult to run that kind of randomized control trial. So I think, particularly we see with kind of Joe Wicks and all the kids doing PE every morning, everyone's on board with that, with a better understanding. I think we have more struggles maybe with looking at sleep and understanding the importance of sleep in learning. Particularly, this is a challenge for adolescents where the school day doesn't move, but their bodies actually want to make them stay up later, and they end up getting less sleep than we think they need for their best kind of mental health, best ability to learn, best physical health. And one of the other projects I've been involved in, which is led by a team at Imperial College, it's called the SCAMP project, where we're interested in how teenagers use mobile phones and tablets, technology, and how that affects their cognitive development and their academic progress. Now, that's an ongoing project. We're just analyzing the data at the moment. It's been running for 4 years, because we've been tracking adolescents, group of actually 6,000 adolescents across the teenage years, and recording how they use mobile phones, how they use social media, these kind of things. But some of the early findings that come out of that suggest that if you use your mobile phone or your tablet late at night, lying in bed in your bedroom before you go to sleep, that has measurable negative impacts on your sleep, how long it takes you to get to sleep, your sleep quality, how much you wake up in the night. And I mean, the interesting finding out of that is you seem to get a bigger effect if you're looking at your phone last thing at night in the dark rather when the light's on.
Mm-hmm.
And the suggestion there is it's to do with the blue light coming from your phone, which is actually triggering your body to think it's still daytime. And that effect is exaggerated when you have the lights out compared to when the lights are on. So that's kind of a really reasonably basic thing, but we have concerns there that teenagers are not getting enough sleep. Their technology usage is exacerbating that, and they're turning up to class for a very, very important phase of their education, feeling quite tired.
Mm-hmm. I want to go back to sort of the things that have been used to sort of develop or improve cognition. And you mentioned mindfulness is one of them. How has it been used in education, firstly? And if so, how has it been used?
Yeah, so again, this is an area where teachers and pupils and parents seem reasonably positive about this, about having time in the class where everyone sits still and listens to their breathing. Clearly, meditation had a big, is associated with religious practices in Buddhism, and it's relatively recent in terms of decades that it's been brought in and thinking in this kind of secular way of just thinking, oh, this is a physical activity we can do to improve our physical and mental health. So some of the scientific questions around that are, so what's the important element of getting kids to sit still, calm down, relax, spend some time listening to their breathing or mentally focusing on some kind of object, a candle or a shape, or these kinds of things we do in mindfulness training. One has to distinguish between, is this something that you're training your mind in a sense? Are you training to improving your focus? Or is it more to do with the relaxation thing? Because we know stress is bad for you. It stops you being open to learning if you're in a very stressed condition. So we have to try and pull apart these two aspects, the kind of mental training aspect and the physical relaxation. The evidence does suggest that the mindfulness part can improve what's called emotional regulation. So how your kind of mind interacts with your emotions and the extent to which you're distracted by your emotions.
So can I just add, I mean, you said relaxation versus focus. They seem to be completely different things. Focus tends to be sort of synonymous with something that's kind of taxing on the mind, whereas relaxation is the complete opposite. So what's the sort of view there?
Yeah, so I mean, it gets into a different area of sort of arousal and stress, and we know that there's this kind of slightly complicated relationship where you need to be in the sweet spot of kind of arousal about being challenged by your learning activities and your tasks in order to be engaged in them, right? If you're too sleepy, you're too laid back, if you're not engaged, you're not going to be in a very good learning condition. But if you're too stressed, you go into that exam and your mind goes blank, right? So that there's a sweet spot about being engaged without being overstressed. And that sweet spot can differ between different children. So we know that there's sort of complexity there. We know some kids in the same classroom are going to be, need a bit of stimulus to get going. But other kids, you give them that stimulus, they become too stressed out. So there is a challenge to manage those kind of aspects. In terms of meditation, it's a relaxed state where you're able to slow everything down mentally and try and observe the pattern of the relationship between your thoughts. And then what happens when you don't have thoughts, and then thoughts pop up, and then they lead to emotions, and then they lead to thoughts and more emotions. And you need to slow everything down in order to observe that. So we think of that in terms of how the brain works as a sort of, you're training your attention to increase your control about the relationship between your thoughts and your emotions. So that's why potentially it can have benefits on emotion regulation, so that you're not being carried away by your emotional state, and you're able to be a little bit calmer under sort of stressful conditions.
I wonder, since you're sort of looking at mindfulness and these sort of concepts of improving cognition amongst, I guess, school children, has there been research done on how it impacts adults and their learning?
Yeah, if anything, most of the research starts with adults. It's more challenging, more fun to do research with kids. Some particularly with neuroscience, where we're using methods of putting people in brain scanners, of measuring kind of brain waves, these kind of techniques, that the research typically starts with adults, and then we try and see whether the same patterns happen in younger kids, and how kids are developing to establish these skills. So I'd say the majority of that research is, getting your expert meditators, your Buddhist monks, and popping them in a brain scanner and seeing what's going on in their brain when they're in the middle of meditation, for example. And then we try and work out from that how it's functioning in the brain. And based on an understanding of mechanism, then we think about, can we adapt this? Can we use this for kids as well?
Mm-hmm.
And then gradually you begin to build up the database with kids. I think, again, the majority of that stuff will be done with adolescents. So the work which is done with younger kids, sort of primary age kids, that wouldn't really be neuroscience work. That will be just saying, well, we think that this could be beneficial to give everyone some space to concentrate, improve their attention skills, to relax. We think that might be useful. Interlude in amongst the school day, which is typically quite exciting and arousing for the children to have some space. And then what we're doing there is running studies to see what kind of benefits do we get. Do the kids just feel happier, or do we see impact on their academic outcomes? And as I say, in order to run those kind of studies, we need to have control groups and comparison groups, and think about how much dosage, how much meditation is right. Every day, every other day, half an hour, 10 minutes. These kind of things that you can only do with careful science to figure out what works best.
Mm-hmm. So you have, we've sort of spoken about mindfulness. We've spoken about exercise. I mean, I follow a sort of pretty well-known neuroscientist, Ramachandran in the US, and he sort of, in lots of his talks, he sort of advocates for people using poetry and comedy and metaphor in improving cognition and improving sort of improving creativity and intelligence ultimately. Has that been an area that's been explored in much detail, or is it still fledgling?
Yeah, I agree. These richer, kind of all-embracing cognitive activities are very important. It's easier scientifically to focus on quite narrow skills because they enable us to have very constrained experimental situations. But you're quite right that integrating, getting many of your parts of your brain working together, and not just the intellectual parts, but with the social parts and the emotional parts, these are very useful to get a broader, more general set of abilities developing in children. Particularly, we teach all these academic skills in class, but ultimately when kids leave school, they need to be able to apply their skills, and to do that in complex social situations. And they need to be able to manage themselves and organize their time and be punctual. And ultimately, our goal is to make them good citizens, which is much more than just having like good math skills or good literacy skills and so on. I think it's harder scientifically to stick someone in a scanner and ask them to come up with new ideas and try and work out which part of the brain is being creative. But that is interesting work. I actually have a PhD student at the moment who's doing a project to understand whether training children's focus to enable them to concentrate more, to be more kind of focused and engaged in a task, whether that's good or bad for their creativity abilities.
Okay.
Because maybe if you're too focused, you can't see these other ideas out there. Or maybe if you can have better focus, you can stay on the creativity task for longer without being distracted, right? So it's not clear whether some of these cognitive enhancement techniques, how they would change your ability to come up with creative poems or to think new ideas. And so these are quite cutting edge areas to try and think much more broadly about how do we use integrated brain function, all the parts working together to do something creative. And as well, part of creativity, so there's brand new out there ideas, but part of it is just problem solving. Here's a problem, you don't know the solution, you need to come up with a creative solution. So these are kind of broader activities where we understand less about the individual component processes in the brain and involved in doing that.
Mm-hmm. So tell me a bit about the difference between learning as a child and learning as an adult. Why is it harder?
Yeah, that's interesting. We recently completed a report for the World Bank, who were interested in examining adult literacy programs in the developing world, in countries where they have, say, the rural poor, and the education system means many of these adults never learned to read when they were younger. And there are programs out there to try and teach adults to learn to read. It's a really good way to escape poverty and to give yourself and your family new opportunities. But on the whole, these programs aren't very successful. And the World Bank were interested in the kind of neuroscience perspective. Is there something they're missing about the adult brain? Is the adult brain just not as good at learning as children? Sometimes we think about children as just kind of sponges. They're absorbing knowledge, and it's just unconscious and intuitive. They're kind of natural learners. Whereas us as adults, it all feels hard and, it happens slowly and so forth. So we spent some time looking into those issues, and some of the results were surprising. So I'm going to say that the neuroscience part of this picture is probably the lesser part. There are many reasons why these adult literacy programs aren't that effective, which are to do with cultural factors, factors like to learn to read, maybe that a conservative estimate says it's going to take you 2,000 hours of practice. So if you go to a 6-month class, like a couple of hours a week, 3 hours a week, by the end of that, you'll have only done maybe 10% of what you need to do to learn to read. So there's still 90% of practice that you need to do at home. But if you're a mother at home looking after your family, you just don't have the time to do that, right? So that there are aspects of this which are to do with cultural constraints and structural constraints and economic constraints, which are not to do with neuroscience. But when we looked into the neuroscience, what's interesting is that adults are better learners in the classroom. And if you think about that, adults can sit there, they can pay attention, they can make notes, they can understand the kind of strategies that you're being told, and they can respond to feedback, and that all makes them better learners, right? So the question is, why do we find it so hard to learn new things as adults? And the answer to that is that what happens is we're not so good at consolidating and accumulating that learning between the lessons. The kids just seem to accumulate and accumulate, whereas for adults, it's almost not quite back to square one, but we lose a lot in between the lessons. And the other thing that happens is it just seems to, in many skills, what we're trying to achieve is something called automaticity. We're trying to do things easily and effortlessly. And that takes a lot of practice to become automatic at skills. And it seems to take more practice for adults than it does for kids to require these kind of automatic abilities. So if you're reading, you don't want it to be effortful and hard. Otherwise, you get tired and you want to give up. Whereas you just want it to be fluid and easy, and the knowledge goes straight in. And then that seems harder to attain for adults and for kids. And that's probably because our brains are changing across our lifespans. We're losing some of our connections in our brain. That's part of what's called an optimization process. Our brains are trying to hone in on what they think, what skills are going to be useful for us in our environment. And part of that honing is to throw away spare resources. And that might make it a little bit harder for us as adults to learn new things. Doesn't mean we can't. It means we have to work harder. But then as adults, we have more complicated lives. And we have less time available. And we all have to think about, are we motivated? I want to learn guitar, age 40. It's going to be hard work. As an adult, do I have the time and inclination to sit there learning all my scales and everything? Whereas I think, actually, I'll just put a record on. That's much easier than playing it myself.
Yeah, that's really interesting. And I want to ask, when it comes to that, I want to ask, so we know adults, from the research, we know adults are better learners in the classroom. But could it be the reason that adults don't retain information as well is the way they're learning? Could it be related to the fact that you're sitting in, like as an adult, the times that you're learning is when you're at university and you're pretty much sitting in a 2-hour lecture or a 1-hour seminar, which is the typical standard. Could it be that as a format that is limiting the learning process? Because I've sort of watched all these lectures about neural chunking and finding all these different ways of learning. So how much has the format got to play with it?
Yeah, the format is important. We do understand that there are different types of methods that are appropriate for different kind of formats. So if you want to impart knowledge, a lecture format is okay. So because you're being given the information that you're required. We know you need to process it. It's good to talk to other people about it. It's good to try and reorganize that knowledge in your head. It's good to think about how you could apply that knowledge to different situations. But that's kind of knowledge-based stuff. But then we know if you're trying to learn skills, there's no point in being told about it. You have to practice the actual skill. So if you want to learn tennis, it's no good just watching YouTube videos or reading the rules of tennis. You've got to get out there and practice on the courts. And there are some aspects of our even our intellectual activities, which are more kind of doing activities than just knowing activities. So it is important as part of what we're trained on in higher education as part of our teaching methods is to understand how to apply the appropriate method of teaching for your learning goals.
Mm-hmm.
So I don't know. I mean, there are different methods. People also differ in how they enjoy or like different methods. Some people like sitting in lecture theatres and they don't mind that, but other people want to be more engaged and interacting. I certainly think interaction is important. That's, as we talked about earlier, that social interaction, if you can have that underpinning the learning activities, will enhance your learning if you can make learning partly a social task as well as just an intellectual one.
Mm-hmm. I want to ask you a bit about your new book, Education Neuroscience Development. Tell me a bit about the book. What does the book entail?
So it's really bringing together the latest research from a wide set of researchers about where we're currently at in educational neuroscience. Educational neuroscience, this is so we've got a new understanding about how the brain works. This has really got off the ground in the 1990s as people developed these new techniques like brain imaging, where we could actually see what's going on inside the brain as people are actually doing things. Very early on, we thought this could be relevant for education, but we maybe started to run before we could walk, and people sort of took up the ideas too quickly. It led to some things called Neuro Myths, some sort of popular misconceptions, things like that we only use 10% of our brain, or that people are left brain thinkers or right brain thinkers. A lot of these things have a seed of truth in it, but aren't really how the brain works. We use all the brain most of the time, and all the bits of it are talking to each other or interacting with each other. So we spent some time in the field kind of consolidating what we do know and trying to help sift from the wheat from the chaff, as it were. And now we're able to present much more clearly what we understand about the important aspects of how the brain learns in different fields, such as literacy, such as oral language development, such as maths learning and science learning, and begin to understand how the emotions are important in learning, how interacting with other people is important, understanding that the human brain has really quite a long developmental period, and it's developing in different ways through mid-childhood into adolescence. We're beginning to understand the important changes in the brain in adolescence that can affect what's important for kids and how they're motivated, and the role of the peer group in adolescent brain development. So the book is really trying to bring together the latest of our understanding there. And also, we talked earlier about cognitive enhancement, this new idea about, are there techniques that can improve our mental abilities? Some of them quite provocative. So those teenagers who are playing hundreds of hours of action video games, there's actually evidence that that's enhancing some of their cognitive abilities. It's certainly improving their visual attention and their ability to respond with motor actions very quickly to visual inputs. at the same time, if they're spending those hundreds of hours sitting on a sofa eating burgers, that part of it's probably not good for them. So there is more systematic research about ways to enhance cognition. And then in the book, we also think about, well, what does all this stuff actually mean for the classroom? So it's quite a long journey to go from some scientific insight into how learning works in the brain to think about, yeah, but how's that actually useful for a teacher who's standing in front of 36-year-olds? How does that turn into a technique that's going to be useful for the particular learning outcomes that the teacher needs? So we're trying to bring together all of that latest understanding and show where the field has moved on to since the 1990s.
And what do you think is ahead for the field? Having written this book, what do you think the future holds for the educational neuroscience?
So there are interesting challenges, some of them technology-driven. So one of the new directions is thinking about genetics and understanding more about that we can differ in our learning abilities because of our genetics. And we can actually now very early on take a read on, measure people's DNA and make some predictions about their potential academic achievement. And that enables us potentially to very early on give parents and teachers rich information about what kind of areas that they could work best with their child, or whether there are any factors around they might have reading problems or maths problems. This is a controversial area, so we're talking about the future, and this is a debate that society is having about how do you use information about one's genome, about one's family origin. How do you use that in ways that don't threaten people's privacy, that empower them, that enable them to use this information for good? So I think part of it is that the future is embracing new technologies. I think in the current pandemic, we've suddenly been thrust into a lot more learning over the internet and the use of technology. And I think that will accelerate our understanding about how technology can be used for the better in educating our kids, and ways in which it really doesn't work. So as I said, it doesn't help to sit a 7-year-old in front of a computer and ask them to learn from a video, whereas that may work for a 15-year-old. So we're beginning to understand more about that, and the integration of technology into learning to augment and help teachers, I think, is another avenue for the future.
And for you personally, where are you going to take your research next?
Multiple lines. The next year ahead of me is trying to write a book on how the brain works for people just beginning at university on psychology courses. I think neuroscience can sometimes be inaccessible because it talks about a lot of different sort of brain areas and the structure of the brain, but it doesn't necessarily tell you about how the thing works. So I'm going to be sitting in this room writing a book over the next year with a colleague of mine, Simon Green. Some of my research at the moment is looking at some of the negative effects of poverty and deprivation on educational outcomes, and trying to contribute to the kind of neuroscience understanding of how is it that poverty is impacting on children's cognitive development and educational outcomes, and can that science tell us something about the ways we could intervene to ameliorate those kind of outcomes, as it were, to close the gaps in educational attainment that are being produced by equality. So that's some of my research going forward in that area.
Where can people find you online?
So again, didn't quite catch that.
Where can people find you online?
Online. We have my research center, the Center for Educational Neuroscience, has a website. So I can zip you the link.
Yes, please. I'll link it on there.
Yeah, Center for Educational Neuroscience. And so we have a blog, we have regular articles on there, we have resources and videos. My own research lab is called the Developmental Neurocognition Lab. And the particular focus of my research lab is to use what I call multidisciplinary methods. That's looking at studying behavior, studying brain imaging, studying genetics, building computational models, running intervention studies. So a whole set of methods, and my focus in the lab is on cognitive variability. So how some people can be cleverer than other people, how some people can be gifted, how some people can have developmental disorders, and trying to understand that at the same time as understanding how, as we develop, we get cleverer. So 6-year-olds are cleverer than 3-year-olds, and 12-year-olds are cleverer. And ultimately, that's a lifespan. It ends up in aging and cognitive decline. So in my lab, we try and understand all these forms of cognitive variability, really rooted in understanding about how the brain develops and how it works.
Are you on Twitter by any chance?
I am on Twitter. I am at MSCTHOM, at MSCTOM.
I'll link that on there as well. So finally, give me a bit of advice for people looking to get into educational neuroscience.
Yeah, so educational neuroscience is what's called an interdisciplinary field, where you're trying to pull together and really bring knowledge and research about education, about psychology, and about neuroscience, and all mix it together and understand whether you can get deeper insights. So if you're interested in the field, do some reading around it. As I say, I've got a new book out. But if you want to get trained in it, you need to start with getting a degree in one of the basic disciplines. So in education, in neuroscience, or psychology. And then as you go forward, you can begin to take your initial learning and link in the other fields. So we have an excellent master's program run jointly by Birkbeck and University College London, a master's in educational neuroscience, where we actually specifically try and do this integration to understand how you can link between education, psychology, and neuroscience.
And it's really important. I mean, this is something that I have discussions with academics all the time about the importance of sort of moving towards this interdisciplinary sort of research, as opposed to just becoming too specific in your field.
Yeah, absolutely. And certainly it's very apparent in our field that this is not a question of researchers coming up with new findings and just saying, well, this is the truth. It's much more about a dialogue, working in groups of people, working with teachers, and trying to understand not just what our findings might mean for them, but teachers telling us where we should be doing our research and where we should focus our energies for the challenges they have in the classroom. So I try and impress that the interdisciplinary research is about a dialogue between people rather than researchers away in their labs coming up with new findings.
Mm-hmm. Well, Mike, I've really enjoyed speaking to you. Thank you so much for joining me, and I hope to have you on there soon.
Great. Thanks so much.